Okay, thank you very much. So we will be starting. So today's session is a workshop. It's part of the three-part Julia Data event during this conference. So today we have a workshop, and it is mostly thought of as an introductory workshop, but hopefully it will be also interesting for people who already have Julia experience. Then we will have a mini symposium on Thursday, and on Friday we have Birds of Feather, and all of this is organized around what's going on with data processing infrastructure in Julia. So we invite you to this, and anyone who identifies himself or herself with the with this organization. Here, Jacob has the stickers for you. And the last thing is from the announcements that if someone is interested in my book, tomorrow I will be at the book booth, and I will have several copies for people who are interested, just to give away. So if you want, I will have print books and ebooks, and you are welcome to find me and get it. So. If you are interested. Because again, this workshop is beginner oriented, let's go everything step by step, as if someone who never worked or at least not worked a lot with Julia would do things. So where can we find our workshop? So if you go to full schedule, let me filter the sessions that are related to statistics and data science, where you can find all the sessions that are in this stream. And here is our working with data frames beyond CSV files. So what we have here, we will discuss how to do data ingestion and writing data in different formats. Of course, we don't have time to cover everything, but we selected formats that we believe are most typically used or useful. And those are divided into two parts. So section one, and this is something I will do till the break, is how to load data from statistical packages such as Stata or R, how to interoperate with databases, and how to read and write Apache Parquet. Then we will have a short break, like 10 minutes break in the middle to get refreshed a bit. And then in section two, Jacob will discuss about things he personally works on. So CSV, Apache Arrow, and JSON. And for both parts, you have GitHub repositories that you can get all the code that we will be presenting. So I will focus on the code that I will present. So let us first try to get this into our local computer. So I will be using today Windows, which is probably popular in Europe. Sorry, not Julia, but not yet. Let's clone this tutorial to our working directory. You have all the instructions how to run the material in the README file. First, a good practice is to just instantiate the repository, and then my part will be using the Jupyter notebook. So it's still cloning. So this is this hopefully will be relatively fast, but unfortunately it's slower than I expected. But soon we will get everything. No, it's for sure too slow, because let me just copy this repository from here we have a list of all the tutorials I did on Julia, but this one is for JuliaCon, so let's go to this tutorial. So what I start with is I start Julia with in the tutorial directory, and I start it with Julia project. And what it does, it activates the project setting for this tutorial. So if I press closing bracket, we can see that this project is activated. I can check its status, and we see that that we have several packages listed. One of them is already outdated, although I have updated the repository 2 days ago, and this is marked with this this green mark. And actually this update is relevant for our talk, but I will go back to it in a second. Now we have started our Julia session, and what we will want to do, we will want to start Jupyter Notebook. So I will show Jupyter Notebooks, and later Jacob will show you how to work with Pluto Notebooks. So let me open the Jupyter Notebook, and you can see that I have 3 notebooks for this session. So introduction, and is part 1. For part 2 is how to work with a bit larger data, and part 3 is potential issues that it's useful to look at. And in this issues, part 3 is actually this update of Parquet, because when I had one of the issues already, this issue was solved after I released my notebooks, but I didn't have time to update the package version. But I think it will be interesting to listen to the story. Okay, so this size should be readable, yeah? Okay, so in my part, as I have said already, what we will cover is reading statistical packages files, and I will use Stata file for this, then reading R, reading and writing databases, SQLite and DuckDB, and reading and writing Parquet. So one of the things that is especially relevant for the statistical packages sources is that they typically support metadata. Also Parquet supports metadata, and actually everything except databases supports metadata. So I will discuss also the metadata aspect of working with tabular data. And if someone is interested in more details in metadata handling, here are 2 links that you might want to check. So it's usually good to start working with a notebook to check the status of the repository. So what we can do exactly the same stuff we did in the terminal. So I'm writing a closing bracket and st for status to get the status of my packages. And what is important is that by default, Jupyter Notebook, as opposed to standard Julia, activates local project repository. So that's why I needed to start Julia with Julia -- project, while this is not needed in standard Jupyter notebook. There are some settings of using Jupyter notebooks. For example, if you would using some collapse spaces or Jupyter notebook in VS Code, sometimes it doesn't get automatically activated, then you need to activate it. But if you are using like a standard Jupyter notebook, as I do, it will get automatically activated. So you don't have to think about activating the project environment. So the second thing we will do is load the required packages. So I will comment on the packages later. So DataFrames needs to recompile, so it will take a second. Actually, it will take around 1 minute. So here also a comment for newcomers why DataFrames takes such a long time to precompile. The reason is that most of the standard functions that normally would Julia compile during their first execution, that they get precompiled during the first load of the DataFrames package, because I had updated my project environment. And after this precompilation takes place, all other consecutive loading of DataFrames packages are around 1 second. And these precompilations means that when we are using DataFrames functions from DataFrames, they are more snappy in day-to-day use. And it is relevant because some of the functions in DataFrames are really complicated, and they could take, without precompilations, like 5 seconds to compile. So without this, they work almost instantly. So as you can see, most of the packages require this precompilation. So this is what we see right now. And once that they get compiled, we will start with working with Stata files. So the Stata file, the file in Stata was taken from the data set that I linked here. This is okay. So probably this is an issue with slow internet connection. So hopefully it will load. Yeah. This is a data set with word development indicators. There are quite a few of them, and this data set is shared with the repository so that you then don't have to download it separately. Yeah, we have all the packages precompiled, and now we can read the data. So if I read the package I use for reading the data from statistical packages is readstat tables, and this package supports Stata, SAS, and SPSS files. And if you just read such a file, which is in our case WDI 2009 DTA, this is an internal format of the package. So as you can see, it's called readstat table. It has some default way it's shown. So it looks similar to DataFrame if someone used DataFrames, but you immediately, at least I immediately see that it's not DataFrame, but some other format. But what is important, and actually Jacob was the person who made it possible, that thanks to Tables.jl, this format is fully interoperable with DataFrame or any other tabular data type in Julia. We can make sure that indeed this is a custom table type with read type, getting type of this, and indeed we see that this is a read stat table. Moreover, as I have said, we can check that this file has metadata. So what does metadata mean? Because this is not something that we have invented in Julia, but this is something that is commonly encountered. So especially in statistics, people attach various information to their data. So in our notation, and again, this is on a Tables.jl level. It's not something that is DataFrame specific, although probably you've heard that DataFrames support metadata, but actually metadata is supported for all table types that want to support it. So first of all, what is plain metadata? Plain metadata is a metadata on a table level. So if I have a table, you can see that some of this information is probably redundant, but it's stored in metadata. So for example, Stata stores in metadata number of rows and number of variables in the table, the date of modification, file format. This is probably also not super interesting for us, and notes such as who and when created this file. So those are various information that describe the whole data set. But then there is another kind of metadata. This is metadata attached to columns. So what is important, we can see that this file is 872 columns, which is, and also if we look at those columns, so first three probably are legible, like country, WB code, which is probably some country code, year is year, but starting from this, and what follows is completely illegible. So, just, AGR track, no, who knows what it is. So, and this is quite typical, especially for example, for data that is wide, and this data is wide, that people start using abbreviations for column names because otherwise it would be not very convenient to work with. But because of this, what is typically done, then you attach metadata to columns, to individual columns, explaining usually what they mean. So for example, this AGR track number, we can see that it's agricultural machinery, tractors, and some other metadata that was truncated. So this is important because in many tabular data formats, you have this additional information also on column level. And my experience is that usually this information is often even more important, especially about labels or meaning of the data. If you have very wide data, probably if you have 2 or 3 columns, this is not super relevant. But if you have hundreds of columns, it becomes important to be able to handle it. So we can, for example, look up what is the column metadata for this specific column. And again, we can see that we have different attributes like label, format type, value label, storage. Some of them are technical, some of them are interesting. Probably label is the most interesting in this data set. So we could work with this table directly, but at least I usually prefer using data frames, especially if the data is not super big. So how to create a data frame out of it? It's simple because I just call a data frame constructor, and because the original data was a Tables.jl table, we didn't need any special code for integration with Stata files in DataFrames. It just happens. Maybe not by magic, but but by common interfaces. So in this way, WDI now is a data frame, not a custom type, and you immediately can see the differences. So, for example, in display, this one is static, doesn't highlight anything, and in this one, for example, if I go through rows, they get nicely highlighted. The display is wider and has the horizontal scroll bar, which again it's quite often important, especially for wide data. While still even if this is wider, we can see that out of those 872 columns, 772 were omitted. So still, it was not everything is displayed by default because it would be too wide, and there is some automatic cropping. You can override this cropping. Maybe the only question or things that people often ask, why don't we by default display everything? Because you could display theoretically everything in a web browser, but there are two problems. First is that you would quickly run out of RAM to display them. And the second thing is that when a Jupyter notebook is saved, then it saves HTML representation and LaTeX representation of every table. So if you had like a lot of them, then your Jupyter notebooks would grow very big very quickly. So we decided on some reasonable, in our opinion, default limits, which in this case it's like 100 columns are displayed, which usually is enough for visual investigation. What is important is that if I create a data frame from that original table, not only data is transported, but also metadata is transported, which means that if I now look at my my data frame WDI, it has table level metadata, which is the same, and also the same way it has the column level metadata. So not only I was able to read in this metadata to work with the data, but also to, if I transform it to another table type that supports metadata, this metadata gets propagated, and if metadata is important for me, I can retain this information. So this is a very basic workflow, and the functionality we provide in reference to Stata, SPSS, and SAS, which in some fields are really used and common data formats. And in them, especially, I highlight this metadata because in them, metadata is very often used to encode important information, and we can get it. So if we read in such source data, for example, I don't know, in medical data analysis, people often use SPSS, and you want to read in this data, this SPSS has some important metadata. You can keep it all in your Julia workflows. So the second type of integration is getting data from R, and I'm saying that it's a second type of information because for this we need a second package. The package is RData, and it's specifically constructed to load R files. So what is the difference? The difference is that if I load a file, here it's cars RData. Cars is the standard table from R, speed and distance. Probably everyone who did some introductory statistics in R. So the cars file. So I decided to have it. What is important to know is that if I load data from R, there are two important things to know. First is that, as opposed to what we saw before for Stata, where we loaded the table, if you load the RData file, actually it can contain many different objects. So if you create RData, you can store in one file several objects, and you can then retrieve it when you load it back in Julia. And here we see that the thing that was stored in this file is only one object that is called cars, and it is a data frame. And the second difference is that we already see here that when we transported data from R to Julia, the R data frame was automatically converted to Julia data frame. So here the difference is that we do not have some custom table type for R. Is just a Julia data frame from the beginning. And the third thing that is important is something that is not visible but was here. So the R files are compressed usually, and you need to install and load a package that is the compressor for the type of compression that was used to store this R file. If you create R archive, you have several options what compressions to use. I used XZ compression, so I needed to do using codecs XZ, because if I didn't do it, I would get an error that that here this loading cannot be performed because there is a missing decompression functionality. So this is something, again, to remember, that if you are reading R data, you need to additionally load a package that does the compression if you used the compression. So let's retrieve. Sorry? So in general, yes. So for example, Parquet also uses compression, but for Parquet you do not have to load it. So you ask about what is the list of standard supported codecs in Julia? Yes. So I don't remember it currently, but I have it in my book because, you know, there is a list of them. So tomorrow when I have the book, we can come and check. And because in the book I give a link to a list to a package that is a meta package for codecs, and then there are specific packages for specific codecs, because in Julia the format of this codecs is that there is one API for codecs, and then you can have different codecs attached to it. So in theory, if something would be really missing, but most of them are all present in Julia, you could write your own from and just provide the same the standard interface for it. Okay, so we extract this cars data frame from the dictionary holding all our objects, and yes, so we discussed about this codec, and what is important, again, R users also know that R tables and columns in a table support attributes. So this, in R terminology, attributes are the same what metadata was in Stata, and those attributes are retained. So again, if your R file had attributes attached to data, those attributes are available in Julia for you. So for example, if I want to check, okay, what was the metadata? So the table level, we have three things: source, which we have exactly here. This is a bibliographical reference for the source of this data, and we see it's almost 100 years old now. Second is technical, which is row names, and third is a comment. So comment, we might want to extract this comment to see it in full. Yeah, actually it is 100 years old, it seems. Yeah, because it was recorded in 1920s. And the same thing for column metadata, which is, and we can see that this is stopping distance in feet, and speed is speed in miles per hour. And I think this is something we added to DataFrames last year, and I think it's really relevant because in many applications users wanted metadata of their data to be retained when they worked with this data in Julia. It was previously not possible. Kind of similar to Pandas, for example, which doesn't support metadata, but in many applications this metadata was needed, and now it is supported everywhere, which means that it's defined on a Tables.jl level, and in particular DataFrames supports it, but it's not something that is DataFrames specific. It's the fact that currently tables allow you to store and process metadata attached to your data. So if you work with your data, you don't have to think about, okay, I have my data and I keep a separate file with some description what this data is. I can just save metadata along with data and keep it in one file. And in particular, what I will discuss a bit later today is that Parquet supports metadata, and there is a full integration of this. So if I saved my data frame using Parquet, this metadata would be stored in Parquet format, and then if I read it back, I will, of course, get this metadata back. And also Arrow also supports metadata, which will be covered, Jacob will later talk about Arrow and what's going on in with this package, because it's pretty actively recently developed, as I see by notifications on GitHub. Okay, so this is the first class of types of data that we might want to work with, which is various sources from statistical packages, like, as I said, Stata, SAS, SPSS, whatever. And maybe in not all, but in certain domains, it is a pretty popular source of data. And I would say, like, a short comment as a summary to this section is that, first of all, we support it. Second, we support it fully, so along with metadata, and this was added recently. And third thing is that I would say that it's easy. So that's why I said that, and we've prepared this tutorial for introductory level users, but I hope you agree that it's like really one line of code, no super big brain needed to just load SPSS or Stata files to Julia, which I think is important because it shows that we don't have a barrier that someone says, okay, I was working with Stata for the last 10 years and now I cannot switch to Julia because I have all my data in Stata. The answer is yes, no problem. You can load it exactly the same way you worked it in Stata, you can use it in Julia. The second class of formats is if we wanted to work with databases. So I chose to show two packages, but actually, as you will see it's pretty similar because, again, for databases, we have one common package for the interfaces, which, again, Jacob is working on this stuff. So it will be SQLite and DuckDB. So the first operation is just to remove the database file if it were present in my working directory. The reason is that I want to create those databases as a persistent storage. The alternatives with SQLite and DuckDB both would be to create in-memory databases, and both packages support it. Then I would just here omit giving the file name in this part. If I give file name, I will create it on disk. If not, I will have an in-memory database, but because today we are talking about storage, so I will be creating on disk databases. So I just create a new database, or I would open an existing database if it with this command for SQLite. I can check if it has any tables, and I expect it should not because I have just created it. So I am querying SQLite for tables, and I see that there is no table in it. And then the question is, okay, first is if I want to use databases, especially both SQLite and DuckDB, I will talk about soon, is a nice format because you have this file and can just share it with everyone, and they don't need to use Julia, whatever technology they use. This is a pretty commonly, both standards are pretty commonly supported. So first what we do is loading our cars data frame into the database, which is done with the SQLite load command, and the first argument is what table I want to load, the second is where, and the third is what should be the table name. So this is how I load a table into SQLite. And now if I run back tables, I can see that indeed our database has one table, and I can see the schema of these tables, which is split and dist. So it seems that loading a table into SQLite worked well. Now I might want to do a reverse thing, so to get out some data from the SQLite table into back into Julia, into DataFrame. So here again it is pretty easy, and it is generic. So here we don't use SQLite specific function because tables was a specific function of SQLite to get a list of tables. Here I'm using DB interface, which is this interface package for working with databases, and execute is a function that executes a query against a database. So here I'm against this SQLite, I'm executing a query to get all rows where speed was less than 9.5 and fetch it into a data frame. So again, if someone knows SQL, this is pretty easy. If I didn't want to filter anything, I would just remove this part, select star from cars, and I would get a data frame. And this is again one line to remember to get back data from SQLite database into a data frame. And what is important, that because this is on a DB interface level, whatever database you would have connected to, it would be done in the same way. you might ask, okay, but what if I wanted to create a table within SQLite without going out to Julia, just from the level of Julia work in SQLite, so you could say like do pushback of whatever I want and stay within SQLite, because it's, in some cases it might be more effective. So the answer is, again, you can execute any query with DB interface execute, which in particular means that I can do create table query and just create some other table in my SQLite database. And now if I create this table without going to Julia, I can see that I have now 2 tables. Now, okay, just technically, again, from DB interface, I am closing this database just to make sure that if I reopen it, I get back the same, so that I indeed got this persistence. So I'm reopening this database, and I can see that indeed I get the same stuff. So we just saw with SQLite that if you have data in Julia, you are working with data in Julia and want to use SQLite format as a storage format for your data, it's again pretty easy to do this. Essentially what you need to know is this load function and DB interface execute function, and you can do pretty much everything you need to do with databases. And again, the important thing is that SQLite is supported almost everywhere. So even if you want to prepare data, I don't know, for working later on a mobile phone, then you can send it, and there are readers of SQLite format on mobile phones, and it's super easy. So SQLite is a database that is mostly designed for transaction data, and that's why I wanted also to discuss DuckDB, which has a similar idea to SQLite, meaning that the idea is to have an easy database that can be used in process. So that I have, for example, Julia, Python, or whatever, and I can run a database. But the difference between DuckDB and SQLite is that SQLite was designed for transactional data processing, and DuckDB was designed for analytical data processing, which means that it will be faster when we perform some columnar operations. And let us see how it works. So first of all, we will connect to the DuckDB database via DB interface connect. And again, because I have passed the file name, it will be a persistent database on disk. I could have also created an in-memory database. So now the one important, that this is a specific feature of DuckDB. How do you load a data frame into a DuckDB table? So there is a specific function in DuckDB called DuckDB register data frame. And why this function is specific to DuckDB? Because if we created a DuckDB database in memory, so not like here that we are making it on disk, but if we made it in memory and we registered a data frame like this, it would not be copied, but it would be reused, which means it would be much more lightweight. Which might be an interesting case if we wanted just to, expose some data to DuckDB and perform some operation, some SQL query on this data that we would find convenient to to perform. So again, let's check if indeed this this table is present in DuckDB. This time there is, at least I didn't find a special function for listing tables in DuckDB, so I'm just executing a query. So the query is show all tables, and in DuckDB, if you run this query, I fetch it again to a data frame, and indeed I get that there is one table called cars in my DuckDB table. So again, if working with the table already stored in DuckDB is identical, so this is a copy paste from SQLite, so nothing new here. I can just do DB interface execute any query against any table I would want, or whatever operation I would like to perform, and then I get the data. Also, what I shown here again, this is exactly what we did earlier, creating a new table out of table in DuckDB without going to Julia, or just fetching the data back to a data frame. So again, we should close the database after we finished working with it. There are two notes regarding DuckDB, maybe three notes. So first that I didn't write is that I recently worked quite a lot with DuckDB. I mean, I switched from SQLite to DuckDB when I need a database, and I really think it works very well for analytical pipelines. So this is a plus. A minus is there is some issue with the close function currently, that the DuckDB process doesn't properly release the handle on the file. So until the mother process terminates, there is a lock on the file. So probably this locking of files everyone of us has seen sometimes. But this is already reported, and it's going to be fixed soon. So I hope this is like a transient warning. And the second thing is that what I have shown you right now is in DuckDB very tightly tied to data frames, but there was a rewrite again in last months of DuckDB where it's been moved fully to Tables.jl interface. So there will be soon nothing data frames specific in DuckDB. It will be the same for data frames as for any table that you might want to use. But it has not been released yet. It is something in the works, but I think it should be pretty soon released. So again, this is something that is, I think, nice. But as a summary for this part, so working with databases, what I think from the perspective of like a regular user of Julia that wants to be sure that you can work with data stored somewhere. If you have data in databases, really this DB interface package is, unless you have really very advanced needs, because then usually things do not have to be easy. But for standard needs, really DB interface and especially DB execute is like everything you need to know to be able to work with databases, as long as you know how to connect to a specific database. So again, I would say that if you have data in a database, if you want to work with it in Julia to analyze it later, it should be really easy and convenient. And the second and the last format that I want to discuss, and we will spend most time on it, is Apache Parquet. So this format is, I think, especially important because it is commonly used for data that is larger than run. And because of this, I will discuss a bit more about how you can work with it. So one particular thing that you will notice already on top is that earlier for databases, I was creating a file, and here, for some strange reason, I am using a directory, not a file. And this is the first important difference that in what Parquet supports, and it's often very useful, you can have your data split into multiple files. So for example, you can have multiple processes that are gathering data from multiple sources. Each of them writes the data into a separate file, but later, and I will show you how you can do it, you can view it as a single data set from the perspective of the analytical process. So that's why I am storing it in a directory, because I wanted to show how to work with it. So let's start with the basic workflow. So again, we have this cars file, which is pretty easy to work with. So this is what I thought is a good starting point. So you can just write a file from your data frame. So you use write file, and in PQ data folder, I am creating cars Parquet file. And now I have written my file. I can read it back. And if I read it back like this, so I am specifying a concrete file in a folder, I get back its information. What is important is that at this moment, if I did this read file, actually only metadata of this file were written. It was not all data of this file, but only its metadata. So it's not important for the cars example, but if we had really huge data, then probably even we couldn't read it into memory. We would need to see the metadata and only later process some chunks of this big file as we wanted. So what can I do? I can read this file, not only metadata, but actually materialize it into a data frame. And this is this thing that that was the update of the Parquet.jl file that up till 2 days ago it was required to, maybe not required, but if we wanted to save memory, when creating a data frame from a Parquet file, I needed to pass copy calls equals false to avoid excessive copying of data. But now it will not be needed because we know that if we are reading a Parquet2 file from disk, it cannot have a second copy somewhere else. So if I know that I am getting this data directly from a file reader, copying is not needed, and this fix has been implemented a few days ago, and I think merged yesterday. And I knew that the fix was merged, but I didn't know that the release was made. So, but you know that in Julia, this release process is really quick. So, soon this copy calls false in order to save memory will not be needed. And for example, if you later see CSV, also it's not needed because it's exactly the same idea that if I'm materializing a CSV file into a data frame, I know that this is the only copy of this data, so it's not needed. So that's why when reading CSV files, also we don't need to pass these copy calls false either. Okay, so you'd ask how it is technically done. Yeah. So are you going to talk about it in the second part? Okay, so because Jacob designed the general pattern, because again, it's a general pattern, these copied columns. It's not something data frame specific. It's just a package can signal two things. Either I don't tell you anything about whether data should be copied or not, and then you need this copy calls true or false, or the package can explicitly message that copying data is not needed. And then you just simply don't need to pass this copy calls false because the package itself signals that copying data is not needed. And actually, that's why this pull request, after I made those notebooks and before the workshop, because I didn't do them today in the morning, but a few days in advance, that's why it was possible to so quickly fix the behavior of Parquet 2, because the whole mechanism that allows avoiding excessive copying of data is generic, again, on Tables.jl level. So, okay, so Jacob will tell a few words about it because it's the same in CSV.jl. So again, as I have mentioned, Parquet supports also metadata. So you remember that in R we had metadata, we read it in as a data frame, it had metadata, but now you see that I saved this file to a disk and read it back and just want to check if it didn't forget my metadata, and as you can see, it did not. So indeed, I went from R to Julia to Parquet and back to Julia, and I still have all my metadata, which is, again, I think nice because you keep some often important information that comes along with your data. So now we are going into something that is a preparation, mental preparation for going out of core. So there is one interesting function in base Julia that is iterators partition. This iterators partition function allows you to partition an object into smaller chunks. So for example, if I write iterators partition cars 25, it means that I want to partition my data frame into chunks of size of 25 rows. So this, now I have, as in display, is just displays that this is a wrapper around a data frame, but what is important that if I, for example, collect this object, I can see that I get a 2-element vector, each having 25 rows. So indeed, I can see that by wrapping a data frame into iterators partition, I made a lazy, because it didn't materialize, but after collection, of course, I materialized it as a sub-data frame because it doesn't copy data. But I didn't, I split my data frame into smaller chunks, which is often needed, and why in particular it is needed in large data context. At least this is my experience. So for example, I sometimes work on a big cluster where I have a machine that has 1 terabyte of RAM. And you know that in cloud you can get such machines. And I'm preparing the data, creating it, but later, at least me, but probably most of us, we want to do something on our laptops, not having to do everything in the cloud. Of course, if you want, you can do everything in the cloud, but you might want, okay, I have created data somewhere, and I want to later be able to easily work with it even on a laptop. So if you have some super big table in the cloud that you know that it will be too big to read back into memory just on laptop, you just do this iterators partition. And why it's important? Because if I write this partitioned data frame into a Parquet file, what I will do in a second. So now I'm writing it to a Parquet file. I have created one file that has a single data frame in it. If I read it back, as you can see, it tells me, okay, it's a data set, 2 columns, etc. If I just create a data frame from it, again, I have 50 columns, 50 rows, so nothing seems to have changed. But underneath, one important thing has changed. Underneath, if I check length of this cars2 Parquet, PQ, so if I check the length of this object, it tells me that the length of this object was 2. So what does it mean? Actually, Parquet knows that I have partitioned my data. So this data is, of course, if I say, okay, fetch me it as a whole, I will get back my whole data frame. But I can say, okay, but now don't fetch me it as a whole, fetch it for me chunk by chunk. So the simplest way in Julia to do it is to add a dot after data frame. So now I'm broadcasting data frame into a collection, because cars2 PK is now actually a collection of 2 row sets, because this is the terminology used in Parquet. So if I call data frame on each row set, I explicitly recovered both partitions of this stored in disk. And why it's important? Because here I read back both partitions at once. But exactly the difference is that I don't have to do this. If I have my data partitioned in Parquet, I can read one partition at a time. And even if the file is 1 terabyte, but if I made sure to make smaller partitions in it, I can just iteratively work with the partitions in this file, and I will show it in a second. Yeah.
So each one of these partitions is very large in memory. You are working on it, and then once it's done, it goes and asks for the next one. Or
no, it's like if the important thing is, if I run this operation, if I run this, nothing is read into memory except 2 things, except metadata, so that we know that there are 2 columns and what is their type, and except that Parquet knows that there are 2 row sets in this file, but doesn't read this data in. So it waits and tells me, okay, I know the structure, but I'm not reading in anything because maybe it's super large. And then I ask, okay, fetch me the first row set, because I could say the following. Okay, cars PQ1. And I have this first row group that has 25 rows. Again, I have the metadata. I have not fetched it yet. If I want to fetch it, of course, I can say, now it will materialize it to a data frame. I can say, okay, fetch me the last row group, or last is not supported. So the second or the left, so not supporting end is another issue to be reported. Because, of course, we know the length, because as we shown, it's 2. So last index will be 2. So, but this is not all. Now let's check if in my directory I have 2 files, cars Parquet and cars2 Parquet. Now what is important that we know that those 2 files, because in both of them I have saved the cars file. Both have the same schema. So both have some object that has 2 columns that are both float. One is speed, second is dist. And now going to the second level, I can say, okay, read me back this directory. If I say to Parquet, read it back the directory, and I can have several options, but the most common is load initial true, which means try reading everything from this directory. Then actually what I learned is that I read in whole directory, and it's still a single Parquet 2 dataset. So again, I could materialize it directly, and probably not very surprisingly, it's 100 rows, because it's 50 rows from first file, 50 rows from second file. But if I checked what is the length of it, it's 3. Why? Because it's 1 row set from the first file and 2 row sets from the second file. So, for example, I could just print everything, and I see that the first row set is 50 rows from the first file, and then I have 2 sets of 25 rows from the second and third file, which I also can verify it with nrow. And why it is important? Because from this you can see that this Parquet format is really very flexible in how I structure your data, my data, because I can split it into multiple files. If I, for example, have several workers working on the same data in parallel, and it's the easiest way for me to distribute it, or even within one file, it can be big, but still within it, I can specify that I want it to be chunked, because it will be more convenient for me later to work with it this way. So this is, I think, quite nice for larger data. So let's do some demo of it. So now I will create some data that on my notebook would not fit. So it would fit probably on some bigger notebook, but this is like a travel notebook. So it's easy to create data that is out of too big to be fit into RAM. So what we will do 2 processes. One process is how to iteratively create such data that you can later work with, that is itself larger than RAM. And then if you have it, how to process it back, so that even if the data does not fit into the memory, how to work with it so that you can do something useful with it. And when we start talking about out of RAM contexts, there are many different flavors that you could consider. You could say, okay, I want a cluster. I want to use multiple threads, etc., etc. But I decided for today just to focus on something, to focus on a simplest scenario. So the scenario, at least when I talk to DataFrames.jl users, this is the most common. User says, I'm working on a notebook, not some super beefy machine, but I'm working on a notebook and I have data that just doesn't fit into RAM. What to do? And again, in this case, probably it's not the issue about multi-threading, etc., but just saying, okay, in single thread, in single process, just help me process this data. And this is the scenario I concentrated on, because first of all, it is simplest, and second, that it is, I would say, most commonly seen. But it is not the only scenario that is supported in Julia ecosystem. And in particular, there will be a talk by Julian Smaro in 2 days about how the tables and Dagger.jl support more automatically what I will show here that is done manually. And about this automatism, I will say in a few seconds. So here what I will do, I will just go step by step, a manual process of working with data larger than RAM. So again, I will do it with Parquet. So first, let's create some data, and this is actually not super relevant what the data is, but I just needed something, so I create a data frame with one column being some mu, and the second column being this mu repeated something a bit more than 1 million times, exactly 2 to the power of 20 plus mu. So we have those many data frames, as you can see here, I'm changing mu from 0 to 1 by 2000, so I have 501 unique values of mu. And this size of data is too big to fit into memory. So if I wanted to materialize all of it in one shot in a data frame, it wouldn't fit into memory on my laptop. So here is a simple pattern. Again, probably we might think or discuss more advanced things, but I wanted to focus on some simple things. How you can incrementally create data that is larger than RAM and still be able to somehow work with it with just data frames. So as you can see, what we do here, for each mu, I am appending the result to some data frame that's aggregating whole data. So df is the data frame that's aggregating all my results from, in this case, some simple simulation. And I'm appending the partial results to this data frame. But I have defined a threshold. This threshold is 100 million rows. And this is the size of chunk that I say, okay, if you get this many rows in your data frame, cut it off and save it to disk, because if you will run for many more rows, you will get out of memory. So how we do it with data frames? So I can check if my data frame has already this max size rows. If yes, then I say, okay, I am writing a separate Parquet file to disk with a view of the first 100 million rows. This is done here. And then I'm just dropping, after writing the files, I'm dropping them from this data frame. And I increase the counter of the file number by 1. And if this is like maybe a side comment not related to the things we do. If I'm writing such things in top level scope, I usually like to wrap them in let, so that my temporary variables do not leak out. And because if I wrap this in let scope, this becomes a local scope, and whatever variables like I, df, max size I define here, they do not leak out outside to my notebook, which is usually, alternatively, I could define a function, but it's convenient often to just have a let block for this. And after the loop is finished, I just need to check, okay, but is anything left in my data frame? If yes, then the leftover also needs to be written to disk. So what is important in this example, the way it was designed, is that, as you can see, I have chunks of size 10 to the power of 8, so 100 million rows, but actually each group is a bit above 1 million, which means that if I'm chunking this, I am not careful enough on purpose to have whole group in each chunk. Actually, when I'm writing these files, now I will have a situation, and it is on purpose, that I have the same value of mu potentially in more than one file, which means that later when I will aggregate the data, I need to be careful to properly perform the aggregation. So we can see that now file writing takes place, and hopefully here it will go through relatively quickly without much delay. Now I can see that there is some delay. I don't know why. Okay, so but let's move forward. So when okay, so I have written 6 files, and now when I read back the data from the experiment, again I'm using load initial true. As I have said, this data wouldn't read in my memory if I wanted to read it all. But first of all, you can see that it's pretty quick to read, and the second one, it doesn't seem that it frees my computer. And the reason is, as we discussed, because now this PQ experiment is like only a view into the data that is on my disk. I can check that this PQ experiment has length 6, so I know that I have 6 chunks. I can check what chunks it has and to what files exactly those chunks correspond to. I can even check without materializing it how many rows each chunk has. And as we can see, first 5 chunks have this 100 million rows, and the last one is left over that I saved at the end. And again, all I'm doing right now, no data was read into memory because I couldn't. I know that I can check the structure of the data, but I'm not reading it in one shot. To read it, I can use any of the functions that allow in Julia to work with collections. And let me, for example, show how to use map. So what I'm doing is I'm doing a map over PQ experiment, so over those 6 chunks, and I'm enumerating them to get a chunk number. So enumerate just makes sure that I have a chunk number and row set. And this chunk number is needed because I want to just show this info that things are alive. Because if you are processing big data, usually you are thinking, okay, did my computer hang or not? So it's usually useful to have this info. And I'm reading a single row set into a data frame, which is small enough to fit in memory. And then I'm doing some aggregation of this row set. And the only thing I make sure is that after aggregation, the object that I actually retain is small enough to fit in memory. So in this case, what I do is just I'm aggregating the data. So I keep the mean of each group and now number of rows that was in this group. So of course, this is much smaller than the original data, like by 1 million times. So I wasn't able to read in all the data, but this aggregated data is something I can store in RAM, assuming this is something that was interesting for me. And here I can see that I have this 6-element vector. So for each source data frame, I have this aggregated data. Now the second step is I can reduce those 6 data frames into one big data frame HG2, and I can see that this data frame has 506 rows, which should be surprising, or maybe not surprising, but I should be careful because I know that I had 501 values, which means that that this data frame does not have all unique rows. And I can check it. And this is column mu. I can check all unique HG2 mu, and I get false, which means that I have duplicates in the mu column. So I have performed aggregation of data, but this aggregation is not perfect because for some cases I have duplicate values. And again, I could say non-unique 2, which would give me the rows for those non-unique values. So this is the default behavior of non-unique 2, non-unique. So I can see that 1938, etc. had duplicates, but this is probably, so this was something that people often complain. So they say, okay, non-unique, what it returns each row that had previously the same row with the same key. But it's not very useful because you say, okay, but I don't know actually where I have those duplicates. So here you have the option to check is, for example, to keep no duplicates. And if I use keep no duplicates, with keep no duplicates, I can now get all duplicate rows. So with no duplicates, actually I keep not the, I keep also this first occurrence, which is, for example, for data cleaning is often useful because then I see side by side all the duplicates, not only the consecutive duplicates. So what I need to do, and actually this is potentially the hard part, is that if I have such chunked data, I need to reaggregate them. So in this case, because this is a mean, this is quite easy, because what I can do is I compute mean of the means with weights proportional to the rows that were used to compute each mean, and now I have reaggregated the data correctly. So what is important here is that this MapReduce process I have shown here manually. In common cases, like computing mean, of course, it doesn't have to be done manually. And for example, Tables.jl would just do it for you. But if you would have a general meaning arbitrary transformation that you would want to do, anyway, no framework will do automatically it for you. So anyway, this process of MapReduce that I have shown, that you preprocess data to reduce its size so that it's smaller, but you retain all information that is needed to later reaggregate the data, is anyway in general needed. But of course, if you have a standard function like, for example, mean, packages can do it for you automatically, and dtables, for example, does it. And as I said, there will be a talk about this on Thursday, even if your data is out of core. Other approaches would be to, for example, use online stats, which again, you could iterate rows and just update the online statistics to keep track of such data. But again, online stats can handle by default only things that can be updated row by row. And other scenarios that I didn't cover is like using multiple threads for in-core data, which is possible, but it's a different topic. Or if I wanted to distribute processing of this data to several machines, again, this is something we have skipped. So maybe to wrap up, let me switch to part 3, which will highlight 2 limitations of Parquet. So One of them we already discussed, and it was solved. And I had a comment, I think, there that it was solved, but there is another limitation of Parquet, which is handling of data with very large number of rows. So, for example, let's create a data frame that has 300 million rows. Yeah, and 300 million rows, if you use Parquet, is too big. Because if I try to save it as a single row set, or this row group, if I try to save it as a single row group, we will wait for a second and Parquet will complain. And this is not a limitation of Julia. If you see this error, this is a limitation of the specification of Parquet, because it was exactly explicitly designed not to allow too big row groups. And that's why actually using these row groups is kind of for big data, not optional, but actually you have to do this, but not by Julia, but by design of Parquet. That the design assumed that you have to do this chunking, but with Julia it is it's super easy because we already know how to do this. You just do this iterators partition, and just instead of passing a large data frame, you say, okay, partition me this data frame into chunks that are small enough to fit. And for example, here instead of 300 million, I'm doing by 100 million rows, and it is small enough not to exceed the limits of Parquet. And again, we will need to wait for a second because it needs to write to the, yeah, it's done. And you can see that now it works. So this is one thing to remember, that you shouldn't, or maybe you should understand the reason for the error. Parquet doesn't allow you to store in one row group too large volume of data. It needs to be split to those row groups, and with data frames and this iterator partition, if you have a data frame that even is very large, it's really easy to split it this way. And the second, this limitation, we already discussed it is memory copying. So this is the previous behavior. So you can see that with these copy calls not passed, we had much more data allocated than with copy calls false. But as I have said, this has been pretty quickly fixed. And this wraps up this first part of the introduction. And again, just to maybe advertise a bit with Jacob, we will say again that after the break, we will learn how it was possible to fix it in one day. And with changing like 2 lines of code so that this excessive copying is not needed. So now let's make, what, 10 minutes break? 5 minutes. So let's just to fix 10 minutes break. If someone has a question to this part, either ask now or I will be here anyway. So you are welcome to ask. I hope it was useful for you. The general conclusion is that whatever standard format of data you would want to work with, it's relatively easy. There are some, corner cases as usual with software, but it's relatively easy. And if you would like to learn more about those technologies for working with out-of-core data, we will discuss it on Thursday. Here I did it like step by step, from the most basic elements, so that you know how it potentially can be manually done. Okay, so thank you very much.